So let me tell you how it works then. You've seen the background. It's obviously based on metric FF. But what we want to do is use our linear program to do this computation of the numeric values, to actually compute the bounds on each numeric value, and also when we're doing solution extraction, we're going to use it to help us. So the propositional RPG is great at the propositional part of the problem. So let's keep that. We don't want to fiddle with that. It's been shown to be very good. It works well. But what we want to do is improve the estimate it can get by using LP models. And the reason that the LP works is it models flows of resources. So from one type to another, if you remember this cyclical resource transfer, it knows if you've unloaded something from a truck, it then goes to being at the location. And you don't have this, it's both in the truck and at the location now. And also, as we'll see, it deals with this problem of helpful action distortion and the problem of freely increasing resources. And this allows us to solve problems with numeric structure that FF just tends to die solving. So that's very useful. So the first thing I'll say is, in order to construct our LP, we have to make some restrictions on what subset of the language we can handle. So if you remember, I was talking about producer actions and consumer actions. LPRPG can't handle any other type of numeric actions. So a producer action is a producer with respect to a given variable if its effect is v equals v plus c. So essentially, it just increments the value of the variable by some constant. That's why c is greater than 0, because otherwise it's going to be a consumer. And it has no precondition v is greater than or equal to minimum. So we can produce is not conditional on the initial value of the variable. A consumer is a similar thing, but obviously it uses up action. It uses up some resource. So a consumer is a variable if it has a precondition v is greater than or equal to c, and an effect v equals v minus c. So it decreases v, but there is some safety constraint that v can't go below a certain value. Or it has a precondition v is greater than or equal to 0, and in effect v equals v minus 1. So this consumer behavior essentially enforces that variables' values cannot go below 0. In the general case in the real world, it's not that useful to have a variable value going below 0. You don't want the number of packages in your trucks to be minus 2, and so on. So we are restricting ourselves to variables that must stay greater than 0. You'll see why we're doing that in a minute. So just to say, you cannot use RPG with problems with other types of numeric effects. So assignment effects, we can only handle one very special case of those, which I may get onto later. So assign v10 is not a linear effect. You can't put that in a linear program, so we can't handle it. The second one is decrease available by wanted. So this would be fine if it was decrease available 10 or decrease available 15 or whatever by some constant, but we can't have a variable decreasing by the value of another variable. And also, obviously this isn't a linear effect, available equals available times 10, but also metric FF can't handle those, so we're not putting any further restrictions in those regards. So let's just have a look then at what an LP looks like when we build it intuitively. So the LP for fact layer 1. The material, that should actually be material prime, is the material at 0 minus the number of produce actions we've applied. Okay, that's fairly intuitive. So because produce decreases the material by 1, then what the material is after is what the material was before minus the produce actions. What's at the store is what was at the store at the start, plus the number of produce actions, because that increases what's at the store, minus the number of load at the store actions, because if we load it onto the lorry, we've got fewer things. And this just carries on for all the variables that we've got here. If you notice these actions here, P, and LST, these are action variables, and these represent the number of times each action has been applied. So this is essentially what we do. Which actions are applicable depends on the actions that have appeared in the RPG by that layer. So we can only here apply produce and load at the store, because these are the only actions we can apply in layer 1. When we move on to fact layer 2, we get some more actions being applicable. Now we can load at we can drive. Oh, and which ones are? Unload at the site, we can unload at the store. So these are two new actions which we can apply. So these then come in the LP, whichever actions they affect. So you see now, instead of having st prime is st naught plus p minus lst, we've got st prime because st naught plus the produce actions plus the unload at site actions, because we now can have applied that, minus the load at the site actions, because that takes values off that variables. These constraints at the bottom, if you remember I said before we have this constraint on the previous slide that the precondition v greater than or equal to c or a precondition v greater than or equal to 0. So these two conditions stop the variable v the value of the variable b becoming less than 0. So we can put in our LP that all these variables here are greater than or equal to 0, because they're the values of the variables afterwards, and we know no action can take them below 0. And also, these are the values of the action variables. Clearly, we can't negatively apply an action. We either apply it or we don't, so we can't have a negative number of action applications. And fact layer 3, again, we get a few more actions being applicable here. We can now load at the site as well, which affects the amount of the number of packages at the site.